today would be a good one for that. Okay, so for in this lesson, we want to start looking at terms to describe simple harmonic motion. So in the event that you're having to watch this from home, this video is for you. Amplitude. The amplitude is what we'd call the maximum displacement from equilibrium. It is measured in meters, unless, of course, we're dealing with the pendulum. So the pendulum would be the radian. So some of you have wondered when you would ever use the radian as an angle measurement. Well, if I'm dealing with a pendulum, I might measure the displacement of the pendulum from the equilibrium position in radians. That is a reason for us to be able to use a radian, not just doing that on your calculator, but we would do that if we're measuring angular displacement for a pendulum. All right, time that it takes to complete a full cycle is the period. And this is missing for whatever reason. Whenever I go through and redo the notes here, some things get missed. So time that it takes to complete a full cycle is the period. You should know the SI unit for that. The SI unit for that is the second. Okay, so when I start talking about periods for simple harmonic oscillators, the SI unit being the second. Now the one that we have not used much at all so far is the frequency. And I don't know if we did that at all when we were dealing with circular harmonic motion. Did we do circular motion? Did we talk about frequency at all? At all? Nothing? Okay. This tuning fork has a 256 stamped on it. Can you guys hear it? I was joking the other day when I said I couldn't hear those things. I could hear a lot of those frequencies, but once I get to about 12,000 or so, I stop being able to hear that. Here's 256. You guys should be able to hear that well. 256 what? 256 cycles per second. So we'll often say CPS is cycles per second, which is the hertz. Right? Hertz is the symbol that we would use for that. So we would say that that tuning fork has a frequency of 256 hertz. Now, because hertz, that's the unit that we'd use, but the hertz is technically an inverse second. So 1 hertz, 1 Hz is equal to 1 over a second. So it's cycles per second. We just say per second. Now, period and frequency are reciprocals. And so since you guys are very conversant with math, you know that reciprocals means that T would be 1 over F or F would be 1 over T. I would like you guys to determine the time that it takes for this thing to repeat. So this is a 256 hertz tuning fork. I would like to know the time it takes for it to go through one of those. Could you do that for me, please? Try it. Frequency and period are reciprocals. So I would like to know the period as 1 over that frequency. If you have a calculator handy, shout that out for me once you get it. Just shut it out and take it to it.
That's 0.0039.
Okay, I want you to see where that 0.0039 becomes seconds, because it's 1 over 256 to the -1 power, seconds to the -1. So that seconds to the -1 would become seconds up there. And so that would be the amount of time it takes for that to complete a cycle. Period measured in seconds, frequency measured in cycles per second. They are reciprocals. Okay? Very small amount of time. Whew. Your egg drop. I just finished up grading some of your egg drop projects that were turned in sort of late. 240 frames per second. If you had 1 frame count, that would have been 0.004 seconds. That's pretty darn close to that. So if your egg came to a stop in 1 frame, that would have been the amount of time it took for that thing to go through one of its cycles. Okay, so we're talking very, very small amount of time. Okay, I'm going to give you some equations for simple harmonic oscillators. The ones on Friday that I went through with you were the mass on a spring. And we did not do the pendulum. We're gonna start looking at the pendulum now as an oscillator. First, I want to check to make sure you understand amplitude. Okay, equilibrium position is 60 centimeters. Julian can sort of see that. The equilibrium position of this thing here is about 60. Place this right here. By the way, in the event that we couldn't see the people that were hitting the bars down there, this is a telescope I was going to use, and it actually works pretty well. I just forgot to bring this thing out. So there's the equilibrium position. I'm going to displace this thing to my left, your right, 20 centimeters. So 60 goes to 80. I'm going to let it go. Turn and tell that person you're sitting next to what the amplitude of that oscillation is. Nope. 20. Amplitude is maximum displacement from equilibrium. So if that's the equilibrium position 60, and then displaced over here at 80, the amplitude would be 20. Okay. Now, I'm going to take it instead of 80. I'm going to take it to 70. Let it go. What's the amplitude? Okay, now turn and tell the person that you're sitting next to you how much more energy is contained when I bring it over to 80 compared to when I bring it to 70. How much more energy do I have there as a factor? Take that, see if you can do that one.
Square.
Would you guys agree there's more energy contained in the larger amplitude? How do you get 4 times, Julian?
The equation x is squared.
Yeah, 1/2 kx squared. Since the energy here is elastic potential, if I double the amplitude, in this case the amplitude would be x, and the 1/2 kx squared, I would get 4 times the amount of energy. So amplitude really does determine the energy of that oscillator. So double the amplitude, 4 times as much energy. All right, let me give you some equations now. The period for a mass on a spring. Not going to derive this for you. Anytime you see a pi, it's related to what kind of thing? What kind of geometric object anytime you see a pi? Circles. You'll see that simple harmonic motion is related very strongly to circular motion. 2 pi times the square root of m over k. Not going to derive that for you. I've done that in years past, but I know I have to go a little bit quicker through this because we have seniors getting out so early. So I'm not going to do that derivation for you. I do want you to notice, though, that if I double the mass, what happens to the period? I double the mass, what happens to the period? It's going to get bigger, right? So here it is with a single car. Here it is now twice as massive. By how much should that period change? Try to tell that person you're sitting next to you. How much should it change? It did not double. Because if I double the mass, all I did was I increased the period by a factor of the square root of 2, which means it went up by about 1.4 times as strong, as big. So I doubled the mass, but it's under square root, right? So twice as massive is not twice the period. How much mass would I have to put on that to get it to be twice the period? I'd have to put 4 things on it, right? So if I take the square root of 4, I get 2. That would give me twice the period. Now you notice the spring constant's in the denominator. If I make k bigger, what happens to the period? It goes down. That means it oscillates more quickly. You might remember I had the other springs up there the other day that was really weak, and so I moved back and forth rather slowly. So Doubling K would not make the period go down by a factor of 2. I'd have to quadruple K. Okay. What if I change G? What if I take this to the moon? I take this to the moon, and I'm going to change the weight of these things. What would that do to the period? Turn and tell the person you're sitting next to you, what would happen to the period if I take this thing to the moon? Mike, you're pretty tall. Sorry, you're pretty tall. Put that on that thing there. Thank you. I have to jump. Okay, now you're going to have a hard time with that. You just move it. Stop that. Don't make it move. Ah! Stop. Okay, thank you. Thank you. I'll take it. Thank you. All right. So I take this thing to the moon. By the way, this is a vertical mass in a spring. That's a horizontal mass in a spring. I take this thing to the moon. What would happen to the period of this thing? Say it again. Thanks. So this one would behave the same here as on the moon, and this one would behave differently. Okay, thank you. I appreciate it. I appreciate your trying. Let your equation be your guide here. Let your equation be your guide. Do you see a G anywhere in that equation? No. Now, what's challenging here is that what I'm doing here is I'm oscillating mass and not oscillating weight. I know that you think I'm oscillating weight, but really it's the mass that I'm concerned about. Now, the mass doesn't change when I take this thing to the moon. Its weight would change. So let's look at its equilibrium position. When I place this thing here, that thing caused it to stretch all the way from where you could just reach it down to here. If I took this thing to the moon and we did that, this thing would be about 1/6 as heavy, which means it only stretches to there. But then when I oscillate it, it's just going to oscillate through a different kind of amplitude, but it would oscillate with the same period. It would be lighter, but it still has the same amount of mass. Okay, so when I go through and you guys are like, ooh, how do I handle this equation? Let the equation be your guide. There is no dependence on G for this thing. Okay. What about if the amplitude increases? I'm going to actually try this one. So here I have a low amplitude oscillation. So measure the amplitude, or measure the period of this. I want you to go through 5 cycles. Okay? Start it when it's stopped at the bottom. And then let it go through and do it 5 times. 1, 2. Okay, did you get 5? What'd you get? One more time. 7.31. What if I make it be more energetic, so I have more amplitude going on? What should happen to the period? What should happen? What's your gut tell you? Your gut tells you it should take longer because it's traveling off rather than correct. But it doesn't. You notice there's no A in that equation. There's no amplitude in that equation. What that means is that the period is amplitude independent. I want you to check that again. Are you ready? So do 5 of those. What was it before? 7.31. Check that again. Large amplitude. It's still going. It'll do that for a long time. So you want 7. You want to get about 5 of those. Within our ability to respond to that. It's amplitude independent, certainly. Okay, so there is no dependence on the amplitude. So 1 kilogram mass. You measured the period to be what? But there were 5 cycles. So how would you get from your 7.19, how would you get to the period? Divide that by 5. I want to know the spring constant for that spring system. Right. So you can do it. What is the spring constant, K, for that system? It's 1 kilogram. And Olivia measured 7 divided by 5. I'd like to know K for that. So what's the spring constant? You guys have to be able to use these equations. That's one of the things. So 7.19, there are 5 cycles. That's a 1 kilogram object. What is K for that? Before you go too far, I'm going to square both sides of that equation. When I square both sides, I get t squared is equal to 4 pi squared m divided by k. That's going to be easier for you to be able to go through and work with that math that way. Okay. Anytime you're working with a square root equation, square both sides, solve for the thing you're looking for, and then you can start to plug those things in. Olivia, you said 7.39? 7.19? Gosh. 7.19 divided by 5. The period is 1.438 seconds. What do you guys get for K? 4 times pi, square that, multiplied by 1. Hey, that's 4 pi squared. And then divide that by 1.438 squared. What did you get? Nice and loud for me.
Well, I don't know if I did it right.
19.
19.
Okay, I did it right.
Okay, 19. Now, what would that be? It'd be kilogram second squared. You guys see that that's what that unit would turn into? Do you guys agree? Kilograms per second squared? What should it be? Should be the Newton per meter, right? K, we said was so many newtons per meter. Is that what we do? Okay, so let's just check that. Is the Newton per meter the same as a kilogram per second squared? Can you check that for dimensions? See if those two things are the same, because they should be. Check it. Is the Newton per meter the same as a kilogram per second squared? See if you can do that. Say it again.
Kilogram per second time distance units. So I'm confused, so we will check that.
Okay, so we got to go back to our base units, right? The Newton is a kilogram meter per second squared. That's the Newton, and then this is divided by meters. Do you see how that reduces to the same thing as a kilogram per second squared? The Newton per meter is the same as a kilogram per second squared. Dimensionally, they're the same thing. Okay. Now, that's the mass on a spring. What I'm going to have you guys do is we're going to also look at the pendulum. Now, a pendulum is a different kind of oscillator. And so I want to take a moment. I have the pendulum set up here so you guys can see it. I think when we were doing energy stuff before, I had this thing up to my nose. Is that true when I did that? Okay, this is a simple harmonic oscillator. The challenge, though, is that the restoring force has to be we have to have a small angle for this thing to be able to work. So it can't be any more than 15 degrees. Anything more than 15 degrees amplitude would no longer be a similar amount of oscillator. Okay, so we got to have a low amplitude. It's called small angle approximation. So 15 degrees or less. Okay, so that's about the maximum amplitude that we get. The equation for it. T is equal to 2 pi. Anytime you see a pi, that means it's related to circular motion. Probably easier to understand how that's a part of a circle than it is the mass on a spring. But all of these things are related to circular motion. The equation for that is the square root of L over G. Okay? I'm going to ask you some changes, some things here. If I make that thing, instead of it being a half kilogram object, if instead I made it a 1 kilogram object, what should happen to the period? So instead of it being a half kilogram, I'm going to make it be a 1 kilogram. What should the period do? Should stay the same. Olivia, ready? Check it. Ready? Ready? Okay, half kilogram. Ready? So, 3, 2, 1, go. 3, 2, 1, go. We're going to do 5 of those cycles. 1, 2, 3. It's like watching paint dry. 4, 5. What was it? 13.31. We change 15. 15. We change it to a full kilogram. What should happen to the amplitude or to the period? Are you ready? Start. What should happen? For this, it shouldn't have any change. Something. Same. Okay. So no change to the period. What if I change G? What if I take this thing to the moon? I'm sorry, G increases, so I'm going to take it to Jupiter. What would happen to the period? If I make G bigger, G's in the denominator, it becomes a smaller period. Okay. What if I make the L longer? What if I make it a longer period? What should happen? That was 15 seconds to do about 5 cycles. How long should I make this thing? What is that? What is the period? Is that about 3? Is that 3? 15 seconds to do 5? How can I make this thing have a period of 6 seconds? Not 3 seconds. I want to double the period. How much longer do I have to make this? 4 times as long. And that's because there's a square root there. This is about 2.5 meters. So if I want to get that thing to have a period of about 6 seconds, I'm going to have to be about 2.5, 5, about 10 meters long for that thing to get to a period of 6 seconds. But if the amplitude increases, it should not affect it as long as I stay below the 15 degrees. Okay? All right. I like it. Folks, that's it. Those are those 2 equations. Now, we have a bunch of things for us to practice, and this is just, you guys are very good with math now. You've been through the 1 semester class, so you should be able to do these without too much challenge. 65 centimeter pendulums, 250 gram bob, swings with an amplitude of 7 degrees. I'd like to know the pendulum's period in Chicago. G is 9.803. As the amplitude slowly, if it decreases slowly due to friction, what happens to the, and again, there's always a mistake on these things here that's supposed to say what happens to the period. It should not change it. I'd like to calculate what the period should be. So again, T, 2 pi, square root of L over G. And I ignore units. I just start plugging things in. I get wrong answers because we do have to pay attention to units. So don't do as I do. Do what you should do. 65 cannot go in that way. So if you're going to make a mistake, it's because of units. What should that be?
0.65.
Should be 0.65. And that's because my value for G is in meters per second squared. So I have to make sure the units match. When I go through and I do that division between meters and meters per second squared, I get seconds squared. Take the square root of that, I get seconds. Okay. So what should be the period there? Shout it out when you have it.
1.68.
At 1.68 seconds. Now, you notice I did not use something up here. I did not use the 250 gram bottle. Notice I did not use the 7-degree amplitude. Now, on a test or a quiz, I'm going to give you things that you don't need. If you start plugging in m times g there, if you start putting in the weight of that object, you're going to get the wrong answers. So you're not going to use everything that's up there. Okay. Geologists will sometimes measure G not using a pendulum like so. They'll measure G using a gravity meter, very sensitive gravity meter. And the idea there is that they're trying to determine what's underneath their feet. Iron ore has a different density than oil. And so geologists will often measure G at various locations on the Earth. I want you guys to determine what the acceleration due to gravity is at that particular spot. So if they're using a pendulum, length is 39.2 centimeters. They measure the period to be 1.26 seconds. I'd like to know G there. See if you can go. Square both sides first. G's in the denominator, so make sure you deal with that. Lifting it up so you can see it, but I've lost the numbers. So if you can shout out for me, what is the L? Because I can't remember it. You shout it out if you would.
39.2.
One more time, nice and loud.
39.2 centimeters.
Okay, so 0.392 meters. I'm going to have this be in meters per second squared. They measure the period to be what? 1.26 seconds. I'm going to square that. And sure enough, I'm getting values for G, the units for G, to be meters per second squared, which is what I should expect. What do we get for that value for G? One more time? Exactly?
9.748.
Okay, 9.75 meters per second squared. That value for G can be very accurately measured by measuring the period. As a matter of fact, this is how we often measure G, is just by using a simple pendulum. Okay? We good? Some new equations. We haven't used these before, but they're fairly straightforward. All right, let's take a look at mass on spring systems. A mass is attached to a spring with a spring constant of 25 newtons per meter and set into vibration with a period of 0.55 seconds. What mass is, and again, I apologize that this didn't all make it on there, what mass is attached. Okay, so again, using period equations, start with the equation. Square both sides. Isolate the variable that I'm looking for. I'm looking for the mass. Once you have it, just shout it out. One more time. 0.194? What unit should go on that? There you go. Okay, our last problem, and again, folks, this is probably where I'm going to stop because I want to do some more stuff with you tomorrow on circular motion stuff, but this would be a good place to go. 250 gram mass attached to a vertical spring causes it to stretch 15 centimeters. The mass is then displaced 5 centimeters down from equilibrium and released. With what frequency does the system vibrate? So, one more time here. Put that back on here. I want you to see how this one is sort of going together here. So you take an object and you place it on that thing, causes it to stretch a given amount. This is its equilibrium position. I'm going to oscillate until I displace it from equilibrium. I pull it down 5 centimeters and let it go. I want to determine the frequency at which that oscillates. How are you going to find K? Which equation would you use? Say one more time. Hooke's law, thank you. Hooke's law, all right. It's all right. I appreciate you trying it. Okay, guys, we've had these equations up here all year long. And the hard part is not doing the math, it's knowing what math to use, right? So we're going to use Hooke's law. It's the one that up here that says the force from the spring is equal to negative kx. That's the thing that's required for it to oscillate. Is that the restoring force tries to bring it back to the equilibrium position. I'm going to find k. I'm not going to have k be a negative because the restoring force and the displacement are always opposite directions. So k is always going to be a positive. K would be equal to the force from the spring divided by x. In this case, that'd be 0.25 kilograms. Multiplied by, I'm here on Earth, so I'm going to multiply that by 9.8 meters per second squared to get the weight of that object. Then divide that by how far it stretches it. So first thing I'm going to do is I'm going to determine K. 0.25 times 9.8, divide that by 0.15. And we get, for K. Shout it out when you have it.
16 and a third.
16 and a third, you said?
Yeah.
So 16.3-ish or so?
Yeah.
Newtons per meter. That's K. I want to know the frequency at which this thing oscillates. There's two ways you could do it. Find the period, take the reciprocal, or you could say F is equal to 1 over 2 pi. Instead of it being M over K, it would be K over M. I don't care how you want to do it. But if they're reciprocals of each other, I could just take my original equation, the T is equal to 2 pi squared root of M over K, and reciprocate that. It'd be 1 over 2 pi squared root of K over M. Either way you do it would be fine. Make sure you have the right unit for it, right? So when you're done, I'd like to know the frequency at which it oscillates. That should be in hertz. Anyone getting about 1.29? Units,
Hertz.
inverse seconds, or hertz. 1.29 cycles per second, or 1.29 hertz. Okay? How'd you do? Get them all? All right. I'm going to stop the video there.